Okay, we'll get started. I just posted homework 2 inside the week 3 module, or the week, what's that? I have it due next Friday, so that's going to be February 2nd at 6 p.m. That's what I have. 1 week from today, we have our midterm exam. Okay, and I guess I'll talk about probably on Friday, because I'm still writing the exam, so I haven't figured exactly what it will cover, but it will probably so far I'll talk about it on Friday. But bring your ruler, okay? It's my favorite thing, right? So the homework this week, or for the neural networks. You'll go through the, download the template, and I try to have you guys walk through some stuff. In the neural network that you're going to create, you have to add some biases to the network, and I'll explain that a little bit later today. I think the homework is challenging but rewarding. I think you will enjoy it at the end of the day. After you get through after you jump through the hoops, I think you'll enjoy it. Okay, we left off on Monday. We looked at the artificial neural network code here. Whoops. Let me see. I guess that's fine. Let me. Load up R here. I made my text bigger because my other classroom got moved to a tiny room with a tiny screen, and the students couldn't see it in the back. So anyway, this is what we have. Okay. And I think we ran through this code on Monday, right? And we got it to work. One part that we did skip over was this area called numeric gradient checking. And so let me just kind of explain what all of that's about. Let me just run through all of this. Okay, so what is numeric gradient checking? The idea here, that's a different class. Sorry, fix my tablet again. Okay, and so if we have just one-dimensional calculus, the derivative is kind of the tangent line, right? So here's your function, you've got a line, and the derivative at some point is just the line that runs tangent to this thing, okay? And the idea here is if we were to zoom in on this location right here, what we would see is you have your function, and the idea is if we went over a tiny bit, some delta in the x direction, and we measured how much, so this right here would be f at x, and this right here is f at x plus delta x. The derivative is going to be equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x, right? So, so that's what we have for the derivative. And for the gradient, it's the same thing for the gradient, but just in multiple dimensions. Okay. So we can say, let's say we have our W matrix. Let's look at our W1 matrix. Our W1 matrix is, 2 by 3. So I'm going to just say inside the W1 matrix, I've got a bunch of 1s. Okay, so what is the gradient of L with respect to W1, and W1 is all 1s. Okay, so this is what we have. And what we want to do is we're going to evaluate the value of L at W1. Okay, so this is our current cost. And then we're going to just add a tiny little delta to one of the values here. Okay, and then we'll have I don't know, what do I want to call this? I'll call this W1 star, and this will just be 1 point. I'm going to just do 0, 0, 0, 1. Everything else is a 1. And then we will calculate the loss function of W1 star. Okay. And so this will be just a little bit different from the current cost, right? It'll be current cost plus or minus some tiny little value, right? So current cost plus a tiny bit of change, plus or minus, a small change we expect, right? Okay, and so the gradient, the first value in our gradient this is going to be some vector, and then right now we don't know anything here. But in this spot, okay, the first kind of the value for the gradient, the first value on the gradient will be equal to whatever that small change is divided by our change in x, which is going to be 0.0001, right? So this is basically the change in f divided by delta x, or in this case delta w of the first spot. Okay. Does that kind of make sense? Right? And so this is calculating the value of our gradient kind of like a little bit manually. It's kind of like we're calculating the slope here as if we just zoomed in really close, and we just did, how much did this part change when we added just a tiny little change to our current x value? Okay? And then so we would do this, and this gives us our first value. Then we do the same thing for all of the other values. We keep everything else to be exactly the same as our original W vector, and then we just change the next one to be this value right here will be 1.0001 or something like that. And then we see how much did it change, and then we would put that value in here. And so this would be a kind of an estimation of what our gradient is. Okay? And what this allows us to do is we can say, well, we're going to find an estimate of the gradient this way, and we will compare the estimate of our gradient to the gradient when we used the formula, right? So on Monday, we did a whole bunch of kind of like matrix calculus to figure out the derivatives or the gradient of W, and W, the derivative of our loss function with respect to W1 and W2. And, we came up with some kind of answer, but, the math was a little bit tricky, and we could have easily made a mistake somewhere along the way. And so having being able to kind of verify what the actual value should be versus kind of the value that we get, we can see if we did our calculations of the gradient correctly. Okay, so the first value on the gradient would be this, and then we repeat for all 6 values. And then we compare. Okay, and so that's what I have implemented in our code in this numeric gradient checking. Okay, so here I'm going to start off with W1 being a matrix of all ones, and W2 also being a matrix of all ones. Okay, and then so we will do we'll forward feed. Okay, and we get the current cost is equal to 0.01532,851. And now I'm going to just add a tiny little bit, 0.0001, 1 times 1 times 10 to the negative 4. This is going to be what I have. Okay, so I'm going to have 1 plus e gives me this. And so here I'm going to have kind of the placeholder. This is our numeric gradient. I'm creating an empty matrix. And we're going to just fill this out. Okay, and so the way we're going to do this is we're going to start off with a matrix of all ones, and then I'm going to add 0.0001 to one of those values. I'm going to do this for all 6. So the first time I'm just doing it to the one in the corner. We go and we calculate the cost after we've added this, right? So here, let me just say I is equal to 1. Okay, and so when I do this, so I start off with W1 being, W1 being this, and W2 being all ones here. Then I'm going to just modify one of these things. So W1 is now 1.0001 in the corner. Everywhere else it's all 1. Okay, and then we go through and I calculate what is, we're going to calculate the cost of using our gradient, okay, versus the current cost was the original cost that we had. Okay, so this is the cost function when I have the 1.0001 versus the cost function when I had all ones. Okay, and we can see it just changed just a tiny little bit, right? So we're going to say how much did it change? That goes in the numerator. So it changed this much, and we're going to divide it by the size of our delta. Okay, and so this is going to be the value that goes into my gradient, 0.0012. And so that's going to go into the top corner, and so my numeric gradient right now is all zeros, and this value goes into the top corner, okay? And then I'm going to do this for all of the other values in my matrix. So I'm going to just do this for 1 through 6, okay? And then when I do that, this is kind of, this is what it gets when it fills it out, okay? We'll do the same thing for W2. We start off, you know, W1 and W2 are all ones, and then we just add a tiny little bit to one of the values in W2, and then we see how much did the cost change, and we fill out the matrix that way. Okay, does that make sense to everybody? Everyone's good with that? Okay, and then so now we have a numeric gradient for W1, and then we have a numeric gradient for W2. So these are what we've calculated when we did it by hand. Okay, not by hand, but when we manually added 0.001 to each value. And then we're going to use the mathematical way of us calculating the gradients of W1 and W2, or the gradients with respect to W1 and W2, when we did all of our kind of matrix derivatives and multiplication. So this was, you know, on Monday we did all of that work to find delta 3 and delta, you know, all of this stuff. And we said, you know, we're going to do y minus y hat sigmoid prime of z3, you know, multiplied by the transpose of a2 and all of this. So we go through this, okay? And this is the value that we have for when we calculated the gradient using the calculus, okay? And so we can see how did the values compare, right? So when we use the calculus, we have 0.013664446. When we did it with kind of the manual method of adding 0.0001 to the thing, this is the estimate of our gradient there. So they are very, very close. And so this, and you know, if we look at this one, we have 0.00121. You know, we have something just about the same, at least as far as the first, you know, 5 digits behind the decimal. So this is encouraging because it means when we use the calculus to calculate what our gradient should be, it matches kind of our kind of common sense intuitive definition of what the gradient should be, okay? And so, you know, we skipped over this on Monday because I was kind of in a hurry to get you to show that the gradient descent works. But this is a recommended step to do, this numeric gradient checking, to make sure that when you did your calculus to find the gradient of a function, that it is indeed returning values that are correct, right? Okay, and here I did kind of like how much, you know, what's the difference between you know, these differences here, and it's the order is quite small. So okay, and then and so we on Monday I showed you gradient descent using the gradients that we calculated. We started off with kind of just these arbitrary gradient values, and then we just said calculate the gradient at each step. So this was the entirety of the algorithm is just using some arbitrary starting points for W1 and W2, calculate what the cost is, use that to calculate the gradient, and then update your estimates of W1 and W2 by taking a step downhill. Once you do that, go back to the top, recalculate the cost, recalculate the gradients, take a step downhill. And then just keep taking steps downhill until you reach the bottom. And then so we did that. It finished, and we got, these were the estimates of y hat. They came out pretty good, especially when we compare them to the original values of y. And you know, the cost is you know, on the order of, you know, in this case almost 0, right? And so if we, oh, I think I messed something up. But anyway, when we kept track of the cost, it just kept going downhill, right? Another option, instead of, so this was kind of our manual gradient descent algorithm that works just fine. R has its own optimization function built in called optim, right? And it employs a variety of methods, okay? And I think, if you took my 102A class, we learned coordinate descent. You could use coordinate descent here. Here we've covered gradient descent, but there's all sorts of other things, like the Nelder-Mead algorithm and things like that. And so the function optim will do that. The function optim, though, requires that we give it a function to optimize. This is the function that we want to optimize, okay? And then it allows you only to enter one object of the parameters. Okay, so here we have there's 9 parameters that need to be adjusted, right? Are 6 in the first weight matrix and 3 in the second weight matrix. And so the way I'm going to call optim is I'm going to give it the parameters, which will just initially start off with 9 random values. Okay. The function that we want to optimize is going to be our cost function here. So let's take a look at how we write our cost function if we're going to implement it into using the optim function here. Okay. So inside the optim function, I enter our data. Okay. So these are kind of just fixed values. This is our data of y and x. Okay. And the cost function is a function of w. Keep in mind here, this w is that vector of 9 values that optim is going to alter. So what we have to do is we have to take those 9 values and split them into matrix W1 and matrix W2. Okay, and so that's what I do here. I'm going to say W1 is going to be the first 6 values in the vector W, and then matrix W2 is going to be the last 3 values in that vector W. Okay, and so this allows us to meet the rules of the optim function, which says I can adjust multiple values and find the multiple values, but all of those values have to exist in one object, okay, or specifically one vector. So here it's going to take this parameter vector of 9 values. It feeds it into the function that you provide it that it is trying to optimize. Okay, and so what we have to do is we have to take that and form our 2 matrices of W1 and W2. And then what is the cost that we are trying to minimize? Well, that cost is found by doing forward feed, right? We multiply our x values by W, and we do the sigmoid, multiply that, so on and so forth. And then the last value, this is the object or the value that the cost function returns, which is just the sum of squared residuals. So this is the value that we are trying to minimize, and that's what optim will do. Okay. Does it make sense how we've rewritten, or how we've written this cost function so that that it runs here? Okay. Technically, because R has lexical scoping, if I did not define y and x inside the function, it would just go and search the global environment for y and x, right? And so technically we don't have to put this in, and we can just count on R's lexical functioning, lexical scoping to take care of that. But in general, it's good practice to have all of the values that you need defined inside the function. Okay, so anyway, if I wanted to use optim, then I can do that. So I'm going to just set seed 1, and I'm going to just call this function for optim here, which says, we're going to start off with some 9 random values. The function that optim will try to minimize is this thing, the cost optim. And then the control, here I'm going to just say do 1,000 iterations. No, I guess I forgot to define this. Okay, and then it's done. So Optim is pretty quick most of the time. And then let's take a look at the results here. All right. So here, this is the minimum value that it found. These are the estimates for W, and let's just see how it did. So what we have to do is we have to take our kind of the vector of parameters that Optim optimized, right? And we have to kind of follow our own rules. And we said, okay, the first 6 values go into the W1 matrix, and then the last 3 go into the W2 matrix. So indeed, we'll take the results parameter vector, take the first 6, put it into the W1 matrix, the last 3, throw those into the W2 matrix, so we can see what our optimal W1 and W2 look like. These don't really have significant meaning to us, but we can kind of forward feed and see what our y hat values look like. And again, the y hat values look favorably, compare very favorably to the actual values of y. Okay. All right. I think here I said a different starting location can lead to different results, and I think after playing around I said I think set seed 10 ended up a little bit different or something. I don't know. Okay, so here if we compare the results of y hat versus y, they were not very good, right? 75 and 85, 75 is pretty good, but 85.2 is not very good, and 89.3 is not very good at all, okay? So here, just setting a different starting location can be, can end up in different results, because you have to imagine the landscape, like you're telling it to go downhill, but depending on where you start on your landscape, you might get stuck in a local minimum and never make it to like the true bottom of the hill, right? Because the instructions are always go downhill, never go uphill, and that means if you get stuck in a local minimum, you're going to get stuck. Okay, Optim. If you look at the help for Optim, they implement some different methods. There's Nelder Mead, BFGS, so on and so forth. So BFGS is the, I forget, it's like 4 people's names. Broyden, Farber, Gold something, Shannon, I don't know, whatever. Okay. They came up with a good method that takes into account like second derivatives and stuff like that. And so anyway, it gives us different things. So we can take a look at the results, and then the minimum value here is quite small. It's on the order of 10 to the negative 15. Compared to when we had the bad starting seed, the minimum value of the cost function was not very close to 0. Okay, so anyway, we have that. Here I said, well, what if I just tried 100 different starting seeds and just see how close we get? And so you can see these are just different. So for 100, so I just had R do 100 different starting seeds, and you can see how good did it go. So the first one, it didn't get very good results. The second one, it got a minimum very close to 0. Here it didn't get good results, not good results. So this 0.0012 seems to be like a common location of getting trapped, right? And then every now and then we'll get results where we've successfully minimized or gotten something very close to 0. Okay. Anyway, that's all of this code. I believe I've posted online for you to take a look at. Okay. And so at this time, I want to introduce, or not introduce, but do the classical like machine learning example of this neural network, okay? And this is the MNIST handwritten digits data set, all right? And if, you know, handwritten digits recognition. All right. Has anyone already played with the MNIST handwritten digits thing? Okay, so if some of you have, okay? I feel like every year, just a few more people. Oh, did I not save that slide last time? I don't know. Well, maybe. Whatever. Okay. Stats 102B, week 3, Wednesday. This is slide 2. Okay. So, okay. This is a while ago, right? This is a while ago. Today, this is like an old example, but it's kind of like one of the first examples where we had tons and tons of examples that were labeled. And so this is like, and the data set is very clean and pure, and this is like a favorite data set for machine learning, okay? Because what we have is, I think, 70,000 examples of handwritten digits. The reason this was created was so that you know, when you have a letter and you give it to the post office, they wanted to just look at the zip code and have a computer route them, because it used to be a human had to look at the zip code and say, oh, this one is going to go over here and this one's going to go over here, and they would have to like sort them by hand, and that was very time consuming. And they said, you know, we can't do this. Can we have a machine do it? And with handwritten digits, it was a lot more complicated than like typed out things, because people's handwriting looks different. So could this be done? Okay. Well, so what we have, so a bunch of people cut all of these digits out and made 70,000 labeled examples, right? That was a lot of work that had to be put in, right? This is like your internship. And so anyway, what they did is we took these digits and we these handwritten digits, they cut them out, and now we have this you know, so someone writes how do I make my pen fat? Okay. Is this it? All right. So let's say this is written here, okay? And so you know, we have this grid of 28 by 28 pixels, right? And each pixel you know, goes from, I think, 0 to 255 for okay. So 0 would be is basically white, and 255 would be indicate black or something very dark, right? And then so anyway, they digitized all of these things. We got 28 by 28, and we just turned this into a vector, right? So now if you do 28 times 28, that's 784. And so each example is a vector of 784 numbers. Okay. And so what we want to do is, can we take this, so this is going to be our input. Can we take this vector of 784 numbers and can we turn this, right? Can we turn it into a prediction of, is it the number 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? So our input is this, and our desired output is going to be, is it the digit 0, 1, 2, 3, etc., 8 or 9. Okay, that's what we want to do. Okay, and so yeah, there's all sorts of ways you can approach this, but because we've been talking about neural networks, and this is a very good, this is a great example of what a neural network can do. That's what we will use. Okay, so we basically just take you know, all 784 numbers, and we're going to just have 700. Maybe I'll go on to the next slide here. Okay, so we're going to set up a neural network. Okay. All right, so our input is a vector of 784 values from 0 to 255. Okay, and so what we will have is in our input layer, we have 784 nodes. Okay, a whole bunch of nodes in our input layer. Okay, then we're going to have a hidden layer, and this I'm going to do an arbitrary. Don't ask me why you picked this, but we're going to arbitrarily say 150 nodes. Okay, and our output, we are going to have 10 nodes. Okay, because our output is going to be categorical. And we have 10 categories, 0 through 9. So our hidden layer, we got 150 nodes. And then our output layer, we've got 10 nodes. Right? And so this, you know, you got all these. So each one feeds into here, and then so on and so forth. Oh gosh, there's so many lines, right? So your W1 matrix, what are the dimensions of the W1 matrix? 784 by 150, right? Okay. And then you have a W2 matrix, which will be 150 by 10. Okay. So you've got all these. Okay, so you have that, right? And then, you know, kind of your input x will be n by 784, right? And then your output will end up being n by n by 10. Okay. All right, is this okay? This is just kind of the setup of our neural network. What we will also do is at our hidden layer, we're going to add some biases. So biases is going to be kind of a vector of 150 values. So right here we'll have biases get added in here. All right. And then we'll also add biases here at our output. okay, before we turn them into to outputs, okay? One thing about our output node is the at the output, each digit is going to be represented with a bunch of zeros and a 1, okay? So if our output nodes are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so this is kind of our output nodes, then if you have the value 7, it's going to be, your output vector should be something like this, okay? And someone might ask, well, why not just use one node and see if it goes from 0 to 1 or something like that, or 0 to 10 or something, 0 to 9. The reason why we don't want to just use one node is because, and if we use kind of the squared residual, then it means if the true value is 6 and we guess a 5, that is, quote, less wrong than if the true value is 6 and we guess 0, okay? Because the distance from 0 to 6 is 6 points, whereas the distance from 5 to 6 is only 1 point, okay? What we want to say is that if the true value is 6 and we guess a 5, that's just wrong. And if we guess a 0, that's also just wrong, okay? We only want to award it points if the true value is 6 and the actual value is 6. And so by turning the vectors into zeros and ones, basically the wrong guess will be, basically have the same distance as any other wrong guess, rather than treating it as a regression thing. Okay, let's see. How much time do I have? Okay, well, let me, we won't get into it, but let me just give you some logistical things, okay, regarding the handwritten data set. So I've added these links, okay? If you want to, I mean, you can try playing around with the code, but we'll look at the code on Friday. This is where you would download these things, and they come in these funny like .gz files. I think someone on Kaggle like converted everything into like a nicer table and stuff, but this is the original data, okay? So it's in these funny .gz files, and if you want to get it loaded into R, there's someone on GitHub wrote this function, okay, called load_mnist, and this will load the mnist data. As long as you put those files into some folder called mnist. Okay, so on my computer, I think I had to unzip or ungz, unarchive these things so that the folders exist here. Okay, so I mean, these files have been up since I guess have been created in 1998. So this has been around for a while, but it's still kind of like our classical hello world example of this big machine learning stuff. Okay, so so you load that up using load mnist, and I think right, let me just clear all of this out. Oops. Show digit, and so we'll load up mnist, okay, and it takes a little bit, but it loads the data into R, okay. So here we have it, and then you can start looking at some of these digits. So we'll look at just kind of this is j equals 2, and if I extract out j, we can see that the label for this digit is 0, and the actual data set is this. So we can see a whole bunch of zeros and then numbers like 252 and 253 to indicate this is where it found something. So this is just the vector of 788 values. This is kind of what it looks like. But then this function showDigit will create a plot, and we can see this is what the digit looks like. Okay, so somebody went through and digitized 70,000, like a team of people did this, right? And so anyway, and we have different things, and so we can just, so right now we can just say, okay, the label is here is 9, and then if we plot the digit, this is what it looks like. And so so we have all sorts of different examples of handwritten digits, and we have, I think, many of these examples. And then so what we'll do is we'll feed this data into the neural network and see if the neural network can properly predict what digit this is. Okay, so we'll do that on Friday.